Good morning, all. Today, we're dealing with a new chapter, laser physics. In this chapter, we have to discuss the following topics: introduction, properties of laser, induced absorption, spontaneous emission and stimulated emission, Einstein coefficients, principles of laser, in that population inversion, pumping, and next different types of lasers such as ruby laser, helium neon laser, semiconductor laser, and neodymium YAG laser. Lastly, we have to discuss the application of lasers. First, we go into the history of laser. We know that laser is a most important optical device developed in the past 50 years. From its arrival in 1960s, it has provided a major development in the field of science and technologies. Especially in digital communications. Laser is an optical amplifier. It is an optical amplifier. We know that the laser, it is an short form of light amplification by stimulated emission of radiation. From this, the word laser comes. So laser is light amplification by the stimulated emission of radiation. From this, we can see that a laser it is a light amplification process. Then in this chapter, when we dealing the principles, we will come across this process. Light amplification by stimulated emission of radiation. And the theoretical background of laser action is the basis of an optical amplifier. It was made possible by the famous scientist Albert Einstein in 1970. When he first predicted the existence of a new irradiative process that is called stimulated emission. So, in 1917, Albert Einstein proposed the radiative process called stimulated emission. This process is the backbone of laser, stimulated emission. And after that, some of the famous scientists done the experiments related to it, and in 1954 a different amplifier, microwave amplifier. The laser is light optical amplifier, and another variation that is called as maser is find out by C.H. Towns and his co-workers. They developed a microwave amplifier based on the stimulated emission of radiation. It is called maser, microwave amplification by stimulated emission of radiation. And the first laser is produced by Mayman in 1960. It is the ruby laser. It is the first laser device. It is devised by T.H. Mayman in 1960. It is a solid type laser. Within month of arrival of Mayman's ruby laser, which gives a deep red light at a wavelength of 694.3 nanometer, and another laser is the first gas laser, helium neon laser. It is developed by A. Javan and associates. They developed this helium neon gas laser within months after the finding of first laser, ruby laser. Helium neon laser emitted light in both infrared and visible. In the visible region, its wavelength is 632.8 nanometer. And after that, several lasers are developed in rapid succession. After the development of ruby and helium neon laser, other devices are developed with different laser medium and different wavelength of emissions. In the later of 1960s, the laser was viewed by the world industry and technology as scientific curiosity. And next we going to discuss the main properties of laser. How can we distinguish between an ordinary light and a laser light? Or how can you distinguish a light from a LED, light emitting diode, and such from a laser? The first point comes to our mind will be the intensity. And what are the other things? Let us check. First one is its directionality. And second is the intensity. And third, the monochromatic. And the fourth is its coherence. Let us check what are they. What do you mean by the directionality? Laser is highly directional and its angular spread is very small. For example, a laser beam can be focused to very long distance with a few divergence or angular spread. Have you got it, the idea? when we flashing some light using any torch, let it be bright light or Mr. Light, anything. Okay, when we flashing it for some long, when we flashing it near to us, it will give only a small circle. Okay, okay, let us consider from this point we flashing a torch, then let it be a 2 meter distance, we will get a bright spot, a circular spot. Its radius or circumference will be very small. Okay, when the same torch is flashed to some distance, let it be about a 20-meter distance, then we know that up to this distance it will increase. If considering it is at 1 meter or 2 meter, then its radius will be 2 or 3 times greater than the first one, or we can say that it is the angular spread. Okay, here if we consider, it is making an angle here, and this angular spread is very greater in the case of ordinary light, and it is very small in the case of laser light. Okay, so laser has a main property of directionality. It means laser is highly directional and its angular spread is very small. And this is important because the energy carried by the laser beam can be collected easily and focused into a small area. Okay, its angular spread is very small, so it can be focused onto a small area. The next property is its intensity. We know that the ordinary light spreads in all direction, so the intensity reaching the target is very less. But in the case of laser, due to his high directionality, the intensity of the laser beam reaching the target is high intense. For example, a milliwatt power of helium neon laser appears to be brighter than the sunlight. Okay, when we measure its intensity and when we compare the light intensity of a helium neon laser of 1 milliwatt power, and when we compare it with sunlight, the laser intensity is more. Next property is its monochromaticity. The term is familiar to you, monochromatic. It simply means it contains only a single color or single wavelength or single frequency. So it is, laser beam is highly monochromatic. The wavelength is single, but in ordinary light, like mercury vapor lamp, many wavelengths are emitted, or in the mercury vapor lamp spectrum, different colors is available. So mercury vapor lamp is not monochromatic, but sodium vapor lamp, it is monochromatic. It is not highly monochromatic because in the spectrum of sodium vapor lamp, a narrow spaced two lines yellow lines is available, but we take it as monochromatic because of it contain only a single color, but there is two line. It is very adjacent lines. Okay, next property is the coherence. By coherence, it means the wave trains of same frequency are in phase. For a light to be coherent light, the electromagnetic wave emitted from that source must be with same frequency and in same phase of vibration. So in the case of laser source is a coherent one. Thus, due to its high coherence, it results in an extremely high power. Okay, this is the main properties of laser. Now we go into the theoretical basis of laser. First, we have to discuss about induced absorption. To discuss the theoretical part of a laser, we consider an atom with energy levels E1 and E2. Let E1 be the lower energy and E2 be higher energy or excited level. We know that a atom is said to be in the ground state. Have you studied about the excitation process, ionization in quantum mechanics in the chapter atomic structure? So in the normal case, the atoms will be in its ground state because ground state is the lower energy state, so it is most stable state. To excite an atom from a energy level, lower energy level to higher energy level, you should give some energy. So consider the figure. Here E2 is the higher energy and E1 is the lower energy state. And now here the atom is in the lower energy state. It is the initial condition. And in this state, a photon is incident. A photon is incident on the system, and this atom absorbing this photon, it will move up into the energy state E2. Okay, According to Planck hypothesis, we know that a photon with frequency nu must have an energy h nu. So this instant photon have energy h nu. It is absorbed by an atom in the energy level E1. Then the atom has energy E1 plus h nu. Then it is reached at the state E2. So what will be the value E2? The atom is initially at lower energy level E1. Then it absorbs an energy h nu. Then the total energy of the atom is E1 plus h nu. Then it is reached at E2. Then E2 must be equal to what? E2 must be equal to E1 plus h nu. Okay. This process is called absorption, or it is induced absorption, or we call it as stimulated absorption. Because why we call it is induced absorption or stimulated absorption? Because of this atom is induced by some photon to go up. Okay, so we called it as induced absorption. Okay, absorption simply means absorbing energy and going to higher energy level. Okay, then the rate of this absorption from the lower level to the upper level, from the level E1 to E2, will be proportional to the number of atoms present in the lower level, or the number of atoms present in the level E1, and also the energy density of the radiation at the frequency. Energy density U of nu. The term energy density is also familiar to you in the quantum mechanics when we discussing about black body radiation and Planck's distribution law, etc. Okay, then this absorption rate proportional to the number of atoms in the level E1 and also on the energy density. Okay, so we can express the number of atoms undergoing absorption per unit time per unit volume from level 1 to level 2 as gamma 1 2, that is equal to B1 to N1 U of nu, because here we say that the rate of absorption is proportional to the rate of absorption is proportional to what quantities? Number of atoms in the lower level and energy density. So as it is proportional to n1 and u of nu, then the number of atoms going from lower level to higher level must be equal to some constant into number of atoms in the lower level and u of nu. That constant quantity is B12. Okay. It depends on the energy levels E1 and E2. When an atom is excited, its stability decreases. So to achieve stability, what will the atoms do? It will eliminate its extra energy. The atom in the higher level must have a tendency to go down. Okay. For that, the atom must emit energy, some energy. So it is emission. So first we discuss the spontaneous emission. So we know that the atom in the excited state will not stay there for a long period of time. What will they do? It comes to the ground state by emitting a photon of energy h nu, and such emission take place one of the following two methods. The emission can be occur in two types, and the first type is spontaneous emission and the second is stimulated emission. And here we discuss the spontaneous emission. In that, the atom in the excited state return to the ground state by emitting a photon of energy h nu spontaneously without any external triggering. Okay, the atom, it is the here the atom is in the upper state. The atom emit and radiation of or radiation or photon of energy h nu, and it goes to the lower energy level. It is the spontaneous emission. And this rate will be proportional to the number of atoms in the higher level, because here no inducing process is occurred. So this rate will not be proportional to energy density. Okay, here the atom emit the radiation h nu. Okay, so the rate of spontaneous emission must be proportional to the number of atoms in the excited state only. It is n2. Okay, then this rate is proportional to n2, and here the number of thus the number of atoms making spontaneous emission per unit time, per unit volume is equal to U21 is equal to what? U21 must be equal to some constant quantity into N2. That constant is A21. Here A21 denotes the transition is from 2 to 1. And here A21 is some constant of proportionality. Okay. And this process is known as spontaneous emission. And such an emission is a random process, and it is independent of incident radiation. And here we discuss only one emission method, and the other emission is stimulated emission. It is important in the case of laser. So the atom in the excited state may move to the ground state by stimulated emission or by other method. Such a method is stimulated emission. Okay. In stimulated emission, the atom going to the lower state by the external triggering or inducement of a photon. Consider here we know that the atom in the excited state, here it is the atom in the excited state. We know that this atom has an energy E1 plus h nu. Okay. As it is in the higher state, it is not stable. But at this instant, the atom is not going downward, by stimulated emission. It is staying in the higher level. In such a situation, a photon is incident on this atom. Okay, then the total energy of the atom must be equal to what? Here first is E. Now its energy is E1 plus h nu, and here another photon having energy h nu is incident on this atom in the excited state. So it absorbs that photon also. Then the total energy of such must be equal to E1 plus 2h nu. So its energy is further increased. So its stability is further reduced. So the atom cannot stay in the higher energy as its stability is decreased further. So it going downward. Okay, it going downward by emitting its extra energy, that is 2h nu. Here h nu is its photon energy. So here 2 photons of energy h nu is produced. So in stimulated emission, two photons having energy h nu is emitted. Such such an emission is called stimulated emission, because the atom in the excited state is stimulated by some external triggering or inducement of photon, thereby emitting a photon of energy equal to the energy of incident photon. So it is called stimulated emission. Thus it results in two photons of same energy, and in the figure its phase difference and directionality also shown. Okay, and in this emission process, the rate will be proportional to the number of atoms in the excited state and also on the energy density. Okay, so the rate of transition to the lower level is proportional to the number of atoms in the energy E2 and also on the energy density U of U. That is, the rate is proportional to N2 and U of U. Okay, so we can say that the gamma 21, it is the number of atom going downward through stimulated emission per unit time per unit volume. That is equal to some constant into N2 and U of. That constant is written as B21. That constant is written as B21 because in the previous case we use a constant for induced absorption is B12, and here the constant is B21. So the number of stimulated emission per unit time per unit volume will be gamma 21 is equal to B21, N2 and U of U. Here B21 is the constant of proportionality, and it also depends on the energy levels E1 and E2. So here we obtained three equations, and the first one is gamma 12, that's corresponding for induced absorption, or that is equal to B12 N1 U of U, and gamma 21, it is the number of stimulated emission per unit time per unit volume, that is equal to B21 into N2 U of U. And the next equation, it was for spontaneous emission, that is U21, that is equal to A21 into N2. Okay, here the constant of proportionalities B12, B21 and A21 are called Einstein coefficients because of this stimulated emission is proposed by Albert Einstein. So we call it the coefficients of proportionality B12, B21 and A21 as Einstein coefficients. Okay. Now I stop here. We will discuss about the Einstein coefficients in the next session. Thank you.